Awesome. Thank you, everyone. So I'm going to tell you a little bit about Rigetti Computing, our approach to full stack quantum computing. The remarks, I think, will cover a lot of breadth, including some of the kind of business aspects we've been jumping into over the last few years as the industry begins to hit the commercialization stage. So just a bit of a background on the company. One of the first things I did when I started Rigetti in 2013 was write down this mission statement to kind of build the world's most powerful computers. And in 2013, and in my career before that at Yale and IBM, people talked about quantum computing, and I think almost exclusively thought of that as a branch of experimental physics, maybe AMO, solid state, et cetera. I always thought of it and wanted it to become a field of computing and of computer engineering. And so by kind of saying, look, we're going to build the world's most powerful computers, the only way to do that is to build quantum computers ultimately, kind of down the road. We kind of set that tone, and we've been focused on that objective ever since. It's always going to be out there on or over the horizon. But at some point within the next decade or two, the most powerful computers in the world will be quantum, augmented or QPU augmented supercomputing systems, and that's the future we're building at Rigetti. We've had a focus on intellectual property since the early days. We filed our first patents in 2014. It takes a long time to get those through, but they'll start issuing around 2017. But we started by kind of figuring out, look, what are the long-term technologies that need to be in place to unlock both the performance, the manufacturability, and the scalability of superconducting qubit technology to get to commercial applications. And the hardware requirements for commercial applications remain a bit of a moving target, but are getting solidified and clarified. The resource requirements tend to look more optimistic year over year, not less optimistic, and that's a really good sign. But they're not fully solidified yet. And the progress on hardware continues to be steady. And it's starting to come from a deep ecosystem of research and development advances, not just in academia, but now moving into industry and into the national labs. So we see a lot of promise going forward for superconducting qubit technology. We started by producing chips at a shared academic facility called the Berkeley Nano Lab, and from that we built a 3-qubit QPU in 2016. We looked around for commercial partners to try to partner with us to work on some of the core chip level process technology like superconducting vias and other things that are required for a scalable processor. We didn't find commercial partners that would have those capabilities, and so we ultimately decided to invest in our own fab, and that started in 2015, 2016. That's been a really substantial success, and from that, in 2017, we released our first 8-qubit processor produced in our fab. When we did that, we were the second company in the world to put a quantum computer on the cloud after IBM. And we've been doubling or kind of scaling the number of qubits ever since. So in 2018, released a 16-qubit QPU, and in late 2019, a 32-qubit QPU. Over the past couple of years, we've started to focus on, in addition to continue to invest and accelerate the hardware development driving towards quantum advantage, which we'll talk about in more detail. We've started to invest in the partnerships that we think are needed to drive quantum computing technology towards commercial utility. And that includes partnerships with DARPA, with the United States Air Force, with Amazon Web Services, where we're a provider to their bracket service. As well as in 2020, we won a contract to deliver the first quantum computer into the UK with Innovate UK. Working on standing that up with Oxford Instruments as a key partner there. As well as in 2020, we partnered with Fermilab on the United States Department of Energy National Quantum Initiative, where we're the anchor industrial partner with Fermilab on one of the 5 US NQI centers. Today, Rigetti is about 130 people, highly technical company, obviously, 40 plus PhDs in physics, engineering, et cetera. So overall, just a overview of Rigetti and our operations and how we see this from a full stack perspective. We've focused on building the foundation for scaling, and that's really from multiple different dimensions: the operational side, the chip technology side, as well as the kind of R&D infrastructure side. So let me start with the chip technology. There's core ingredients that are needed at the chip level to enable scalability. That's been a bit of a theme here. We focused on getting that process technology in place and learning how to manufacture chips within that architecture that addresses the long-term challenges. And that's meant kind of not kicking the can down the road on solving some of those scaling issues. It's not, excuse me, I certainly would not say scaling is a solved problem. I think what's happening right now is that we're starting to get a handle on the challenges that need to be addressed and beginning to solve those problems. And we feel good about our chip technology in that regard. From the operational side, this industry is going to look a lot like the semiconductor industry in the end. It's going to be about design, fab, test cycles, about running wafers, getting data. And so we've invested heavily in the R&D infrastructure to ensure that we are in a position to kind of rapidly do the development work, get the data, and run the kind of development flywheel that needs to happen. On the, a critical ingredient here is actually connecting real quantum computers up to the cloud and running end user programs. In the NIST era, and probably in the what I'd call the kind of partial error correction era that's going to follow it, algorithm development and application development that is really needed to unlock the commercial opportunity and to really get the industry going is going to continue to be empirical in nature. Complexity theory analysis is an essential component. It also needs to be paired with hands-on development, and much like has happened in the development of artificial intelligence and machine learning techniques over the past few decades. That's how quantum computing is ultimately going to unfold and come to the market. And so getting these machines into the hands of end users, whether those are folks in the high performance computing ecosystem, like our partnership through Oak Ridge National Lab, or into the more general purpose computing world through AWS and the public clouds. That's an important aspect of driving the product development towards practical use cases. And then the third part is it's extremely important to engage with real world applications and to partner with the organizations that have those important end uses, because they're the ones that are motivated to actually work with companies developing the technology and to partner with them over to address the challenges and risks over the full stack of capabilities that are required to address those problems. This is a shot of the inside of our quantum computing facility in Berkeley. Each one of these DIL fridges is either a test and development platform where we'd be turning it every week or so and getting data off new designs, new process variations from the fab, or potentially a deployment system. Today we've got one machine in deployment at any one time. That's been up and down. We expect to increase the number of deployed systems going forward. And a big part of that R&D infrastructure is just the ability to rapidly design chips with high quality design tools, run them through the fab, package them, and get them into these fridges for high quality data, testing and get high quality data off the chips to address the challenges going forward. This is a shot of the inside of our fab. As I talked about, we invested in the fab starting in around 2016. It's been one of the most important strategic initiatives for the company, and it is a core driver of kind of progress and solving the engineering problems that are needed. Ultimately, everyone here knows the hard thing about the hard thing in quantum computing is building the quantum computer chip, and that starts with fab ultimately. And we've started to now branch out with the fab and use it as a platform for research and development partnerships. So there's through the NQI Center with Fermilab and some of the other Department of Energy entities, we're able to use the fab to test process ideas or materials research ideas from a broader research community, and it's really first of all, it's great. It's great for the company, great for the team, and great for the overall progress in the industry. Here's a bit of our summary view on the pathway to fault tolerance. Obviously, long-term, large-scale, universal error-corrected machines is where the industry is going. There's probably different points of view on the timeline to get there. It's going to take some time, and it's not going to happen anytime soon. These are going to be incredibly complex and sophisticated and very large machines. And there's a couple of steps I think that are going to be important between now and then, and each one of those is going to relate to an acceleration in the rate of growth of the industry overall by beginning to unlock some of the early use cases, or getting tangibly getting closer to some of the high impact problems that we expect quantum computing to be able to solve eventually. Right now we're kind of at that NISQ era, and quantum supremacy and what we call weak quantum advantage. Obviously, Google's had the profound demonstration of quantum supremacy, and it's something that's an extremely important milestone in the field. We're focused on what we call weak quantum advantage, and this is slightly different. It's ultimately where you're solving a practical, operationally relevant problem. And doing that with some degree of advantage over traditional purely classical solutions. So it might be cheaper to solve it using quantum computing or a quantum augmented workflow. It might be faster, or it might be higher accuracy solution. In weak quantum advantage, and how we think about that, weak QA is when you're able to demonstrate that practical benefit on a real operationally relevant problem, but it may not be supported by a complexity theory separation in the algorithm you're actually running. So maybe you're using quantum computing to run sampling more efficiently, but it's not necessarily highly transferable. It may be a sharp use case where it's demonstrated and hard to transfer. Now, down the road, we think of strong quantum advantage ultimately as where you're leveraging a supremacy-capable workflow, or a supremacy-capable subroutine, something that has a provable complexity theory separation between what's possible classically and what's possible with quantum computing, and applying that to solve a practical problem that is operationally relevant. And in that case, we would expect the demonstration to be highly transferable, to be reproducible, and to be enduring. And ultimately, that's likely going to require at least partial error correction to get to that strong quantum advantage. And there's been really great progress on this over the past couple of years, thinking of ways of potentially doing error correction on just the Clifford operations and other approaches to that. And ultimately, that's going to be the stepping stone then that unlocks some of the commercial opportunity and gets a step closer to fault-tolerant quantum computing. As you go kind of each step up and to the right here, the error rates decrease, fidelities increase on all your operations, the physical size and the number of qubits in the systems increase, and the overall complexity grows over time. And that's kind of matched with, hey, it's further out in time. The market size for the end use applications are growing to begin to kind of continue to support the overall investment and scale that's needed to get to these milestones. And then the rate of industry growth is going to accelerate with each one of these as well. So the way we think of commercializing quantum computing, in a little bit different approach here, is there's kind of three ingredients that you really need. Right now, the industry is dominated from an end user perspective, ultimately by the pursuit of quantum advantage. That may be benchmarking systems to truly understand the sources of error or the error models that dominate in contemporary hardware. Or running toy instantiations of what will eventually become operationally relevant problems, and learning how to integrate the technology into an existing computational workflow, whether that's a problem encoding or more generic IT factors, like how you make the compute accessible to a particular, within a particular environment. So there's and to continue to drive the progress here, we need better performance, more qubits, higher fidelity. Improved stability is a very important factor that needs to improve in order to unlock the commercial opportunity, and more accessible systems. So ways of integrating QPUs into existing compute infrastructure, whether it's HPC or public clouds, and driving the accessibility. More and more easy to learn programming languages, I think, is really important, and some of the investments that have been made throughout the ecosystem in Circ or QuizKit and some of the other programming languages is extremely important in driving this. And then there's the kind of problem framework and helping potential end users with those high value applications. We said solve some of humanity's most important and pressing problems. So where are those problems, and beginning the process of understanding how to articulate them in a way that can be represented for some degree of quantum acceleration through a computational workflow. So today, Rigetti has been operating QPUs over the cloud since 2017. Today, we're at what we call our 32 qubit node. That node has been in production. And by that, we don't mean we're building dozens and dozens of copies of those machines. We mean we've got a machine available on the public, on Quantum Cloud Services, on our cloud offering. So we've got a 32 qubit node in production. Typical performance metrics are shown here. One of the things we've focused on at Rigetti is trying to establish a tone for the industry of transparency around actual performance of systems. And so at the bottom of the slide there, you can see a link at which you can get live real-time stats on the currently deployed systems. And those numbers may be different than what's on the slide because these systems recalibrate at a regular cadence. And every time you recalibrate, the numbers might be a little different. And so you can go there, qcs.rigetti.com, and check out the real-time performance of the systems that are deployed on QCS. We think that's a really important thing going forward to help the ecosystem understand the true level of performance that is available across the industry today, as well as to just give people the knowledge to design practical algorithms in the NISQ era and error mitigation and benchmarking techniques. So I want to just shift gears a little bit here and talk about some of the scaling technologies that I believe are really important going forward and that we've been working on at Rigetti. First and foremost, kind of at the high end of chip manufacturing in any industry, in CMOS, in the semiconductor industry, at the high end of chip manufacturing, things are yield limited. And that's not any different in quantum computing. In fact, yield is one of the most important problems that the whole industry kind of needs to focus on solving. Today, we're at such a small scale that this can get swept under the rug. But going forward, to solve both the yield challenge as well as to make the systems highly manufacturable, we have focused on developing a modular QPU architecture and improving out some of the core ingredients of that. So what we mean by that is the idea of assembling a multi-chip module quantum processor onto a single kind of cap wafer, if you will, or cap die, but based on multiple quantum ICs that would be repeated units, where the quantum ICs house the qubits and have the Josephson junction containing elements. So by doing this, you can master the manufacturing of the repeated unit, the quantum IC, that has the yield challenges at a smaller scale. And those yield challenges are always exponential. It's the nature of how it works and why it's so hard. And by being able to do that at a smaller scale, you can then master that manufacturing, really dial in the design and performance at that scale, and then leverage the benefits of lithographic-based manufacturing to produce many of these smaller dies on a 6 or an 8 or 12-inch wafer eventually, potentially. Today we're on 6-inch wafers. Then assemble your quantum computer from those units, from those repeated units. So what we've done is actually proved out the ability to generate high quality entanglement and 2-qubit gates across these chip boundaries in the same way that we do for intra-chip, 2-qubit gates. So this modular QPU architecture, what we've shown here is a 4-silicon die build, which is derived from our 32-qubit Wilson system that is available over QCS today, and built a variant of that where there's 4 interchip edges, 4 interchip gates across each of the 3 edges between 4 dies in the image at left. Then what we've shown is the ability to simultaneously generate quantum entanglement across each chip edge. And proving out through an entanglement witness, there were kind of 10 standard deviations above the classical limit. We can do high quality gates. In fact, the conclusion from this work we're able to show is that it's hard to distinguish the interchip gates from the intra-chip 2-qubit gates. There's no net new challenges in the fidelity or the gate times and materials engineering there. So that's a really important technology going forward. Because it combines a lot of different factors. There's several things that need to be working to do this demonstration. And this was reported in a paper from Allison Gold et al. Earlier this year. Ultimately, this is one of the early steps in building out that modular, fully entangled quantum processor architecture. Another key technology here is just accelerating the 2-qubit gates. One of the extraordinary things about John and the Google team's supremacy demo was just how fast the 2-qubit gates are. And so we took a look at what we're doing. Our 2-qubit gates are typically in that kind of 100, 200 nanosecond time frame, and want to find ways to accelerate them. Over the past couple of years, we've been able to demonstrate using what we call parametric resonance gates, so modulating the frequency of a tunable qubit in such a manner that its average frequency lines up to the qubit you're targeting to entangle it with. And by doing this, it's derived from core technology that we've had and we've been working on for several years, but a modification of that. Then we've added in tunable couplers into that architecture. And by doing that, we've been able to show 99%, north of 99% 2-qubit gate fidelities in about 44 nanoseconds for an I swap gate. So those times aren't quite as fast as what the Google team has achieved, but it's making a lot of progress and it's getting closer. So when you combine this with the high fidelity, the one, T1 and T2 that we typically are able to demonstrate even in our integrated kind of large, 16, 32 qubit processors, we expect to get a lot closer to that coherence limit and to the, close to the requirements needed for quantum supremacy on these systems. Really quickly, some of the problems in the nearer term, kind of in the NISQ and then weak QA era and into the partial error correction era that we think are going to have promise for quantum acceleration. I won't go through all these in detail. Combinatorial optimization is an important one. And it's a known approach. We're going to talk about it in the next slide. We're going to talk about our DARPA program a little bit. It's important, and it's probably one of the most well-studied application areas for NISQ era quantum computers or partially error-corrected quantum computers. Machine learning and AI continues. It's actually making really fast progress on understanding where there may be accelerations by applying quantum computing. One of the places we're particularly interested in is generative modeling, which relates a little bit to Monte Carlo as well. So with Monte Carlo, where you're basically using the quantum computer to potentially accelerate or increase the performance of a sampling algorithm to drive Monte Carlo simulation, could have really, really important impact in computational finance and other fields of stochastic-based simulation. And solving systems of linear equations is again, there's been some algorithms, hybrid algorithms on this. It's unclear exactly how they scale and if they're going to be able to show a strong or weak quantum advantage, but there is some promise there. And the reason that's interesting is because obviously solving systems of linear equations, even if it's in a very reduced domain or a small fraction of the overall space of linear system of equations with a high degree of constraint around that would be highly impactful because of the generic application of that kind of computation. So we have partnerships and programs that are aimed at helping, at building partnerships that drive the technology towards these use cases and leverage our full stack vertically integrated approach. On this DARPA ONISC program, which stands for Optimization on Noisy Intermediate Scale Quantum Devices, we partnered with NASA, the Quantum Artificial Intelligence team at NASA, and USRA to co-design a full stack system guided by the requirements of solving complex scheduling problems of interest to DARPA and their customers. Last year, when the United States rolled out the National Quantum Initiative, we partnered with Fermilab and we're part of the winning team for one of the 5 United States National Quantum Initiative centers. That's called the SQMS Center, or Superconducting Quantum Materials and Systems Center. We're the anchor industrial partner with Fermilab. This program has just been incredible. There's 81 PIs across 20 different partner organizations, truly some of the best and brightest in the quantum computing broader research ecosystem, as well as a wonderful set of industrial partners from Janus to Goldman Sachs and others, Unitary Fund, are involved in this program. And ultimately, we see this as an opportunity to align many stakeholders across the disciplines and kind of into the overall root system of research and development that's happening to drive quantum computing technology forward, and for Rigetti to play a key role as an industrial partner in that. The overall goal of the program is to achieve a systematic understanding of the sources of decoherence in superconducting qubits using both 2D and 3D cavity-based architectures. And then last year, we were part of the team that kind of lead on the team that won this contract with the university, with the UK government, to deliver the first commercial quantum computer into the UK. We're currently in process of standing up the machine at a site with Oxford Instruments. Other partners here, the University of Edinburgh is working with a wonderful research group there, is leading an effort to develop quantum verification and benchmarking techniques for supremacy capable quantum computing systems. And we're working also with Standard Charter on generative modeling techniques for quantum machine learning applications into computational finance. And Phasecraft also under this program on quantum simulation. So you can see from the approach here that we like to partner and we like to work with other complementary organizations to drive the technology forward. And with that, I'll wrap up. I think I'm a minute over.
Yeah, you are a minute over. So
yeah, great, just on time. I'll just finish here. We're hiring. I'm sure as a lot of organizations have, we've evolved a little bit since COVID and some of the requirements there. So we've moved to a kind of hybrid on-site and remote culture at Rigetti, and it's been a very fun and exciting transition. And so we're hiring in California, we're hiring in the UK, and we also have remote roles available. And so if you're interested, wherever you are, please get in touch. We'd love to start a conversation. And if you're interested in a partnership or collaboration on any of the topics you heard today or other things of interest to you, we'd be thrilled to connect with you. So thank you so much for the opportunity, and look forward to questions.
Thank you very much. We have a question. We have time for one question, Nathaniel.
Yeah, thanks. So one I think question that comes to mind is regarding the interchip connects. I mean, can you again explain what the difference in the physics of these interconnects and the interconnect between qubits that is on chip?
Yeah, I can. There's no difference in the physics, and that's the important point. The capacitance is formed using something that looks very similar to the intra-chip capacitances that kind of instantiate the couplings or form the couplings between the qubits. From a physics perspective, it's the same. The qubits can't particularly tell that there's a silicon boundary. From a simulation-driven design perspective, you need to take care of some other factors because there's an air gap between the silicon chips. But ultimately, those are not physics factors. Those are certainly engineering and design factors. It's ultimately the same couplings and the same kinds of 2-qubit gates that we run across those boundaries.
Okay, thank you very much.